Hey folks, today we're going to start talking about electric circuits. And specifically today we're going to talk about, reality. And that being everything has resistance, including batteries and wires and so on, that you can't eliminate in a real life circuit. So let's say, okay, so the title I put on here is battery EMF. Okay, EMF is short for electromotive force. And it's an old fashioned term that basically describes the force that moves electricity, electromotive force. But what we're really talking about is a voltage. So, EMF, if you see the term EMF, that is a voltage. Okay. Now, let me explain kind of what that means. So let's say you have yourself a car battery. Now, if any of you are familiar with cars, a car battery is rated at 12 volts. Now, they're actually a little more than 12 volts, but I'm just going to go with 12 volts here and keep it simple. That's the EMF of the battery. That means if you have nothing plugged into the battery at all, and you were to hook up a voltmeter to that battery, it would read 12 volts. Okay, so this would be the EMF of the battery. However, if you actually plug something in, like a light bulb, let's say, like your headlight, it turns out that the headlight won't get all 12 volts because every single power source has some internal resistance. In the picture there, I'll call that little r. Okay, that has to do with the physical makeup of the battery. Also, like you can count the wires that go from the battery to your headlights. If you're in your house, this would represent maybe the wires that go from your outlet to whatever you're trying to power, a lamp or hair dryer or whatever. Okay, and then you're going to actually plug something in. Okay, so we'll get at a resistance capital R. We're going to call that R sub L. L stands for load. That's the thing you actually want to power. So, like if it's your car, it might be the headlights, or maybe it's a radio or windshield wipers, whatever. Now, if it is headlights, by the way, the symbol for a light bulb is the resistor symbol, but then they put a little circle around it. It just kind of represents the glass going around the bulb. Now, how much voltage would actually be at the headlights? Okay, so if I were to plug a voltmeter in here, what would that voltmeter read? Well, it's not going to read 10 volts, right? It's going to, or 12 volts. It's going to read a little bit less than that. Now, let me give you some numbers just so we can play with them. Let's say this little resistance here was 0.5 ohms. So that was half an ohm. And let's say your car headlights had a resistance of 10 ohms, just to throw a number at it. Okay, the symbol for EMF is a fancy looking E like that. Okay, so knowing Ohm's law, V equals IR, okay, the total voltage of your circuit is your EMF. All right, that's going to equal our current times our total resistance of our circuit. Now we have a zero point 0.5 ohm and a 10 ohm. I'm going to write that as little r plus RL. Okay, and we can factor that out. So E equals IR plus I times RL. Okay, so in our circuit, this is 12 volts. Well, this will be less than 12 volts. Okay, um, so let's go ahead and kind of figure out those numbers. So the current would be your EMF, which is 12, divided by your total resistance, which is the sum of those two resistors. So in this circuit, this would be 12 divided by zero point 0.5 plus 10. And if you work that out, you get 8 sevenths, which is 1.143 if I round to there. That would be amps. Okay, so that's your current flowing through your entire circuit. Okay, so that's your current. Now, if I back up now and see, okay, so what's this voltage at the load? So the change in voltage at the load would be that current I just got. That's our 1.143, and then times the resistance of the load, which is 10. That would be 11.43 volts. Okay. What that also means is the voltage that's lost. So the voltage, eaten up by that little resistor, and I'll call it delta V, would be 12 minus that, which would be 0.57 volts. Or you could have taken the current times 0.5. That would have given you the same answer within rounding. So now, by the way, notice the total is still 12. Okay. So here's what that means. If you have a 12-volt battery, in this circuit, the way it's hooked up, okay, the voltage at the load will be 11.43 volts. And you're losing due to internal resistance, which you have no control over, you're losing 0.57 volts. Okay. The lower this resistance of the load, the more current will flow, and the bigger this voltage will be, which means the less this voltage will be. So, for instance, you may have noticed this at home. For instance, when you turn a vacuum cleaner or a hair dryer on, those are two good examples. When you turn a vacuum cleaner or a hair dryer on, those draw a lot of current. Their resistance is rather low, and they draw a lot of current. So, a lot of current comes out your wall socket. Well, if a lot of current's flowing, that means you're losing some voltage due to the internal resistance of the wires and such. Therefore, anything else that happens to be plugged in at that moment will lose voltage as well, so the lights will dim. So, like if you're in your bathroom and you turn your hair dryer on, you'll notice the lights in the bathroom will dim slightly. This is why that happens. Same with if you turn a vacuum cleaner on at your house, the lights will dim around you. Another example at my house is when a sub pump turns on, the rest of the house dims ever so slightly because we're drawing more current, and so we lose some voltage in that internal resistance. Now, one other thing to figure out about this is, what if I wanted to get the max power to the load? What resistance should I make my load to get the max power there? Now, you have competing ideas, right? The lower you make R, the bigger the current, the better. But the bigger the current, the less this voltage is. So there's some competing ideas here. So in order to figure out the max power, we're going to figure out the power as a function of RL, and then we're going to maximize that. So you might recall that there are three versions of electrical power. So power at the load, you can use I times V of the load, or you can use I squared R of the load, or you could use V squared over resistance of the load. I'm going to use the I squared R one. I'm going to use that version, but any of those three would work here. So we have an expression for I. It's E over the sum of the R's, okay? And then we got RL. So let me write this out. So power to the load is equal to I squared. So that would be all this squared. So that would be E squared over little r plus resistance of the load squared. And then times that by RL, resistance of the load. Okay, so that is our expression for power as a function of RL. Well, how do you maximize anything? Well, you take the derivative of it and you set it equal to 0. So I'll call the derivative, and I'm going to rewrite this just to make my derivative easier. So you get E squared times RL times little r plus RL to the -2. So I'm going to write that way. So the derivative of this, you can write it dp drl, okay, the derivative of this. So if you recall from calculus, you're going to take the derivative of this times that plus this times the derivative of that. Okay, so here we go. So the derivative of the first part would just be E squared. Okay, and then you multiply that by R plus RL to the -2 plus this first term, so E squared RL times the derivative of this, which would be little r plus RL to the -3, and then times that by -2. So it's the exponent times this, and subtract 1 from the exponent. So you get that. Okay. So negative, it's like, so in other words, if I asked you to take the derivative of x to the -2, it would be -2x to the -3. Okay, that's we're doing the same thing here. Okay, so now we need to get common denominators, so I'll rewrite this out. So you get E squared over little r plus RL squared, and then this will become a minus, right? 2E squared RL over little r plus RL to the third. All right, so if I get common denominators, I got to multiply the first fraction by little r plus big R. So if I do that, I get E squared times little r plus RL, and then the other term will be minus 2E squared RL, and then it's all over. Our common denominator is little r plus RL cubed. All right. And then if I FOIL this out, okay, you get E times little r, or E squared times little r, plus E squared times big R minus 2 E squared times big R. And so what happens is you get the following. You're going to get, you can factor that E squared out. Okay, remember that's the battery voltage if there's no load. And then you get little r minus RL up there. And then in your denominator, you get little r plus RL cubed. Okay. Now, if we want the max value of the power, we want to set this derivative that we just determined, we want to set it equal to 0. So in order to make this 0, what does RL have to be? Well, RL has to equal the internal resistance of your circuit. So if I wanted to get the most power possible to this ball, I want to make the most heat there, okay, I would want to make this resistance 0.5 ohms to match that. And then I would get the most power there, okay? And then you can plug numbers in and you can get an actual answer for what that power is. All right, I hope that video was helpful, and thank you very much.